That looks more like a title slide.
Yeah.
All right, can we get started, Zahra?
Yes. Let's get started.
Perfect. Welcome back, everybody from lunch. So our next speaker is going to be Zahra Kadkhodaie. She's a grad student at NYU, advised by Iris Simoncelli. She's taught quite a bit about generalization and diffusion models, generalization and memorization. So she'll tell us something about it today. And Zahra, please take it away. Because it's a Zoom call and Zahra can only hear us through the microphone, I'm going to sort of stand somewhere in the back and mind the room. So if you have a question, just raise your hand and I'll come and shuttle the microphone to you. Please take it away, Zahra.
All right. Thank you for the introduction. And I want to first apologize to everybody for not being able to be there in person. I hope it doesn't affect the talk too much. All right, so let's get started. In the beginning, I'm going to talk about this recent work in a collaboration. It's a collaboration with Florentine Guth, Eero Simoncelli, and Stefan Mala. And if I have more time at the end, I'm going to talk about like a related topic to generalization with the same collaborators. All right. So we have all seen really high quality images generated by state-of-the-art diffusion models. Here I'm showing you a bunch of those generated by a diffusion model. So, and we have been told that diffusion models learn densities of images through data. Now, the question is, how is that possible? We have learned that it's almost impossible to learn densities in high dimensions because of the curse of dimensionality, which says that the number of data points that you need in order to learn a density in high dimensions increases exponentially with dimensionality. So how is it that diffusion models are doing this? They give us samples of images. One possibility is that diffusion models are simply memorizing the training data set. In that case, the learned density is just a collection of delta functions. And in fact, several recent works have shown that this is what is happening in some of the state-of-the-art diffusion models. So on the left, I'm showing one example from the literature where the generated sample is almost an exact replication of an image from the training set. And on the right is another example of a different work where on the bottom row, we have training images which are very close to the generated images, or they're replicated in regions of the generated images. So this is evidence of memorization in diffusion models. Alternatively, another possibility is that diffusion models are able to interpolate between the training data points and actually achieving a continuous approximation of the underlying distribution of the data. So they might be generalizing beyond the training set. So now the question is, which one of these two strategies do they take? And the answer to that, the short answer to that is both. Sometimes they memorize, like I showed you, but sometimes they are capable of generalizing. So because the interesting case is generalization, we're going to focus on that and ask, how is it that they can generalize despite the curse of dimensionality in high dimensions? So that was basically the motivation. So now let's look at, like, very quickly, look at how diffusion models work. Just a reminder. So diffusion models are built from denoisers, deep neural network denoisers, which are trained to remove Gaussian noise by minimizing mean square error between the output and a target clean image. So here in my notation, they take the noisy image Y, which is the sum of a clean image X and a sample of Gaussian noise Z. And then they return an estimate of the clean image, which is f hat of Y here. And the standard deviation of the additive noise changes in a wide variety of regions. It goes from 0 to 1, for example. So then, after the training is completed, this denoiser is applied to an initial sample of noise iteratively and partially until an image is generated. So here I'm showing an example from a denoiser that has been trained on a face data set. And so everything that I'm going to show here is a variation of a diffusion model, which we developed a couple of years ago. All right, so now the question is that why does this work? What does denoising have to do with sampling from a density? The magic lies in this equation that connects the density to the denoising mapping. So this is attributed to Tweedy and Miyazawa. So basically, it's very simple. What it says is that from a Bayesian perspective, we know that given a noisy image, the best estimate is the conditional mean of the posterior distribution. Which is this integral. We can rewrite this integral in terms of the gradient, which is what Tweedy and Miyazawa did, which is great, first of all, because we don't have to deal with an integral. Working with gradients are easier. But also it's very easy to interpret. It's exact. It's basically telling us the optimal one-shot solution to a denoising problem is basically going uphill the gradient or following the gradient of the log of the P of Y, starting from the noisy image. So this is the connection between the denoising performance or the denoising mapping and the density. However, there is a little mismatch here because this is the density of the noisy images, not the density of the clean images or the prior that we are interested in. So that connection is also simple. Because we just added two independent random variable, X, the clean image, and Z, the sample of Gaussian noise, their distributions are going to convolve. And as a result, P of Y is just a blurred version or a diffused version of P of X. And the level of blur or diffusion depends on the standard variation of the additive noise. So when we train a denoiser on a wide range of sigma, we are creating a family of scale space representations of Px, which is analogous to the temporal evolution of a diffusion process. All right, so now this is the optimal denoising solution and its relation to P of Y. When we learn a denoiser, this mapping, the neural network, estimates F star, which was the optimal denoising, which we're notating here by F hat, and the gradient of the learned prior, whatever which is embedded in the denoiser. So now we can use this denoiser as a gradient machine conveniently, in order to use in this algorithm in a coarse-to-fine gradient ascent manner to start from a sample of Gaussian noise and sample an image from this density that is embedded in the denoiser, or this family of densities. This was a quick review of, like a simple review of the diffusion models. Now, the question is, what we observe is not the density itself, right? So we only have direct access to the samples from this density that is embedded in the denoiser. Now the question is, what is the type of this density that is embedded in the denoiser? What kind of density the network has learned from data? Or in other words, is it just a collection of the delta functions, like, or the training examples, which is what we expect because of the curse of dimensionality? Or is it a continuous model of the underlying density which can generate novel samples? So to answer this question, we're going to design an experiment. So we want to study the behavior of the diffusion model as a function of the training set size. So we train 6 denoisers on increasingly larger training set sizes, starting from 1, the extreme case when there is only 1 image in the training set, to 100,000 images. So now we have 6 different diffusion models. And then we're going to draw 1 sample from each one of these diffusion models, starting from the same seed. And here I'm showing these samples. All right, so now we are going to go back to each respective training set and find the closest sample to the generated sample, like the closest training image in terms of the Euclidean distance in pixel domain. And I'm showing those closest images in the training set to each sample on the top row. So as you can see, when the size of the training set is small, like when it's 1, 10, or 100, the generated images are exactly replications of the training examples. So we have like memorized prior. But when the size of the training set increases to 100,000, the generated sample is not a replication of the training examples. It's a novel example, and it's high quality. And in between, there is a transition phase where the generated images are either low quality, or they are patched together from different training samples. So for example, here, I'm not showing you another training examples where this generated samples is getting this corner from. So now we're going to repeat this experiment, but with a new batch of data. So we have a new set of face images, which we have not used before. We train another 6 networks. And so we have 6 new diffusion models, and we're going to generate samples from these 6 new denoisers from the same starting points, from the same seeds. And here on the 3rd row, I'm showing generated samples by these new diffusion models. All right, so now we can go back to the training sets that we used for these models and find the closest images to them. So the 4th row shows the closest images to those generated samples. So again, for small training set sizes, we have memorization. But surprisingly, for the largest training set, not only we have a novel sample, but this novel sample is pretty much the same as the sample that was generated by the previous model with the same training set size. So although we trained these 2 denoisers on 2 different non-overlapping data sets, they ended up learning the same denoising function and the same density. So basically, the model variance has converged to 0 in this case. So back to the original question, do diffusion models memorize or generalize? The answer is both. They memorize with little data, as you can see here, with a small training set size, and they generalize with lots of data. So we have shown in our paper that this is not just an anecdote. If you rerun this experiment with many, many seeds, you end up seeing this phenomenon every time.
A quick question.
Yes.
Why are seeds comparable across the 2 models trained on different training sets?
Because we want to start from the same point in the space. And
Oh, sorry. By seed, you mean the random initialization of the model?
yes.
Okay. Yeah.
Oh,
okay.
no. I mean the initialization of the
Of the diffusion.
trajectory. Right.
Yeah, of the diffusion trajectory. That's what I meant to say.
Yes.
Yeah.
Yes.
But are you also using that seed for the diffusion process, or that, I mean, there is randomness in the diffusion process itself.
Oh,
and
yeah,
it seems
good
like the
question.
seed would interact with totally different parameters in different ways. So I find this
Yes.
quite surprising.
Yeah. So this is surprising, but so that is true. We have two sources of stochasticity in the diffusion model. One is the starting point, and the other one is the injected noise in each iteration. So here for these experiments, we are matching both. So
Thanks.
in both cases, the stochasticity is the same.
In Zahra, the two sets are completely disjoint, like set A and set B are just
Yes.
completely disjoint.
Yeah, so in the pre-processing phase, we basically made sure that the similarity, the cosine similarity between images does not pass a threshold. So we dropped images which were too similar.
Couple more questions there.
This is really interesting. Can you comment on the size of the model that is being learned and how that relates to the samples and the transition? Yeah.
Yeah, that is a very good question. So this 100K number totally depends on the size of the model and the size of images, and also probably the complexity of the data set or the distribution. So that is the second part of the talk, which I thought I would go to if we have time. But like the short answer is that when you have smaller images, obviously you need less samples. And with larger models and larger images, to generate larger images, you need larger models, so they grow together, and then you will need more data in order to enter generalization regime.
Hi, thank you. Sorry, I'm a massive fan of your work, and this is so cool.
Thank you.
So you mentioned that sets A and B were disjoint. Would you expect that they were sampled from the same underlying distribution? Like, were they taken from the same overall training set?
Yeah, exactly. Yes, that was the assumption, which I didn't really specify yet.
One more second, Zahra.
Yep.
Hi, thanks. I also like it a lot, but I have one question regarding understanding. So you sample from these two models, and then you get the same phase, but how can that be? Because normally, like if you draw random variables or so, even if the underlying distribution is the same, you're not going to see the same realization, right? So
Right.
How can that happen? So I don't get it. Is that some mode collapse?
So that
thing
is no. So this is basically, imagine that, because I have like, I think a figure coming up. Imagine that we have the sampling process is not stochastic, and the stochasticity is only coming from the initialization. So if you start, then in that case, it's easier to understand that when you start from the same point in the ambient space, if you have the same function, so if the model variance is 0, then you have the same functions learning coming from these two different data sets. If you apply that iteratively to the initialization point, you end up on the same point. It doesn't indicate mode collapse. Because we are getting rid of the stochasticity, basically, by matching the initializations and the additive noise.
We're out of questions for now. We'll let you continue.
I'm partially observable.
Oh, okay, sorry.
So one more question. Have you thought about other ways of checking how the similarity between the two p-hats that you learn through basically these two different data sets, other than just generation of samples?
Yeah, so this is the most strict form of similarity, because we're looking at the cosine similarity. And this is what we are interested in, because we're interested in the model variance, basically. Like we want to literally learn if you're learning the same denoising functions for different noise levels or not. So that's why we're looking at the Euclidean distance.
Just also to make sure that I'm somehow like following what is maybe the most surprising fact here. So in some ways, because you're trying to do distribution matching, you wouldn't be as surprised if you learn two push forward maps that basically get you the same distribution. But somehow like here, you're literally learning the same push forward map, as in like the same Gaussian sample gets mapped to the same image. Okay.
Yeah, exactly. Yes. So yeah, which is not surprising in the limit of infinite data. Which would be what we need, because these images are 80 by 80. And they are 8-bit images. So you can imagine that without any hypothesis, we will have 256 to the power of 6400 states, possible states in a histogram of images, right? So in order to, without any hypothesis, to estimate this histogram in a brute force manner, you will need infinite data, because that's almost infinite.
But even in the infinite data is a little bit surprising, right? Because somehow there might be, I mean, like there's invariances, right? So you can take the same Gaussian and there could be like, two push forwards, even at infinite data, that give you the same image distribution. So,
I see. Yeah. Right. You're saying that, yes. Yeah.
I think now we're really out of questions. You can continue.
Okay, good. All right. So now it's a surprising result. So, and that basically, before going to the next question, this is where we've shown that, or at least we've tried on a different data set, bedroom Elsoon data set, and we observed the same convergence, pretty much around the same number, 100,000. And so this phenomenon is robust to the change in data set. And we have tried this for a different architecture. So the previous architecture that I used was a UNet, which is the more common architecture for denoising nowadays. But before, I've used a BFCNN, which is an older CNN model for denoising. And again, we see the same phenomenon for convergence. Here, the images that I'm showing are 40 by 40. They're smaller. So we see the convergence much earlier at 10,000 images. All right. So now the question is, well, this is very surprising. How is it that we achieve this generalization? How is it that with limited data compared to what we actually need, we can generalize? And basically, it seems like the network has really good inductive biases, which are aligned with the underlying distribution. And those inductive biases lead to early generalization. So now the question is, what are those inductive biases? So in order to study those inductive biases, we're going to go back to the classical framework of denoising, because at the core of the diffusion model, there is a denoiser. So we need to try to understand the denoiser. So what is the classical framework for denoising? It's basically shrinkage in a basis. So most of the classical traditional denoisers worked in 3 stages. The first is to transform the noisy image into a basis where noise and signals are separable. Then the noise is suppressed using some sort of a shrinkage function. And then the coefficients are transformed back to the pixel domain. So this is a very simple framework. The difficulty lies in finding a good basis where the noise and the signal are maximally separable. So when we apply the shrinkage function, we don't lose a lot of the signal, and we don't preserve a lot of the noise. So the basically the decay, the rate of decay of the coefficients, or the compactness of the coefficients, the compactness of the representation of the image in the basis gives us an idea of how good the denoiser is. All right, so let's look at a few historical examples here for denoising, which you might have all heard about, just to make the connection to the DeepNet. I'm going to briefly mention them. So the first denoiser, like effective denoiser, was a Wiener filter. In this case, the noisy image is taken to the Fourier basis. So the basis is fixed. And then on average, there is a difference between the representation of noise and signal or images in the Fourier domain. So if the noise is white noise, it has the same power in all frequencies on average. And then this is an empirical fact that images have a 1/k spectrum in Fourier domain because of the prevalence of smooth regions. So there is this statistical difference in the average representation of images and noise in Fourier domain, and we basically, the Wiener filter takes advantage of this difference and designs shrinkage factors where the low frequencies are kept and the higher frequencies are suppressed or shrunken more aggressively. So whatever lies below the noise level is suppressed more aggressively. So this is basically a Wiener filter. And the point here is that it's a shrinkage in a basis where the shrinkage function is fixed and the basis is fixed as well. So fast forward after 50 years, with the wavelet model, emergence of wavelet decompositions, we realized that coefficients fall faster in wavelet domain. Image coefficients fall faster in wavelet basis. So that was better because now we can make better denoisers. But on top of that, people came up with adaptive shrinkage functions instead of fixed shrinkage functions. So that improved the denoising performance even more. So here is an example, a simple example of an adaptive shrinkage function, which is adaptive thresholding, which basically tells you that there is an optimal threshold where everything that is above every coefficient above that threshold is going to be preserved, and everything below that is going to be set to 0. So now it turns out that we can interpret the deep neural network denoiser as a shrinkage in a basis where both the shrinkage factors and the basis are adaptive. So let's see how it works. The denoising mapping is locally linear. So f hat is locally linear. So for any given input, we can rewrite it as the Jacobian with respect to the input times the input. And we have shown in previous work that this Jacobian is nearly symmetric. So we can rewrite it in terms of the eigendecomposition of the Jacobian. So this is how the shrinkage in a basis works. We take the noisy image, or the DeepNet takes the noisy image into an adaptive basis, which is basically the eigenbasis coming from the Jacobian, and then the coefficients are multiplied by the eigenvalues, which are normally between 0 and 1. So they act as shrinkage factors, and then it's going back to the pixel domain. So in this case, we have shrinkage in a basis, but both the basis is adaptive to the image, and the shrinkage function is also adaptive to the image. And this is why the DeepNet denoisers are so powerful, because of this adaptivity. All right, so now let's look at an example. Here we have like a test image. Again, we have a denoiser that is trained on a database of faces, and we have a test image, and we do the eigenanalysis and look at the eigenvalues. So it has a fast decay. The eigenvalues have a fast decay, which means that the representation of the image in the eigenbasis is compact, which is good. And now we can look at some of the top eigenvectors for this image. These are some of them. They are adaptive to the underlying image, so you can recognize some parts of the underlying image in the eigenvectors. So if I change the image, I'm going to get a different set of vectors. So they're adaptive. And the second thing to notice here is that we see oscillatory or harmonic patterns along the contours of the face and in the background, foreground regions of the image. So because of these two properties, we call this type of basis a geometry adaptive harmonic basis, or GABS. All right, so this is all qualitative. But based on this observation, we build a hypothesis, which is deep neural network denoisers have inductive biases towards learning gaps. So basically, there are denoisers that do shrinkage in these geometry adaptive harmonic bases. And by having inductive biases, what we mean is that they learn gaps whenever it's the optimal thing to do, but they also learn gaps if it's not the optimal thing to do, because they're inductively biased toward learning these solutions. So how can we now test this hypothesis? In order to test the hypothesis, we need to know what is the optimal basis for denoising for each class, but we don't know that for natural images, right? And probably we will never know that. So we have to resort to synthetic images to answer this question. And here I'm going to show you two cases, two classes of synthetic images. In the first case, gaps are actually the optimal denoising basis. And then we're going to look at the behavior of the trained CNN for denoising for this class. And then we're going to look at the second class where gaps are not optimal. And then also we're going to look at the behavior of the deep net. And we'll observe that in both cases, the basis that is learned is a gap. Okay. So here is the first class. These are called geometric C alpha images. They're basically, they consist of regular contours on regular backgrounds. And the level of regularity increases with this factor alpha. So mathematicians have shown that the optimal basis for denoising these images is a form of gap. And they have worked out the optimal performance for that denoiser. Now let's look at the deep neural network denoiser from a diffusion model. So here we trained a deep neural network on C alpha images for denoising. And then we're going to do, or we have shown, I'm showing a eigen analysis of an example test C alpha image. And you can see the top eigenvectors of the basis for denoising this, the noisy version of this image. So as you can see here, the harmonic patterns are more prominent here. They are more easily observable, both along the contour and in the background foreground regions. So this is in the right direction. It seems like the CNN is learning the optimal basis for denoising. However, this is still qualitative. We need a quantitative result. So thankfully, mathematicians have worked out the optimal performance in terms of the slope of this plot. So what is this plot? This is a denoising performance plot in terms of input PSNR versus output PSNR. So higher values are better. Each curve is associated with a denoiser for a different alpha class. And as you can see, the optimal curve, which is the dashed line, is matching the empirical curve, which is the solid line. So this shows that the deep neural network denoisers achieves optimal performance in the gap spaces. So DeepNet is capable of learning gaps for denoising when it's the optimal solution. So this was the first test of testing this inductive bias. All right.
Super
So,
sorry.
yeah.
Sorry. How
Yes.
many images was that model trained on for the C alpha?
Yeah. So now we are in the generalization regime. So this model and the next one that I'm showing you are above 100,000 images, the training set size for them.
Gotcha. Thanks.
Good. You can carry on.
All right. All right. So now the second class that we consider is the class of these disks. So we have a data set, we generate a data set of disks. These data set is generated using 5 parameters. So all images from this data set lie on a 5-dimensional curved manifold. So what are these 5 parameters? It's the vertical and horizontal position of the disk. So the disks are translating, the radius or the size of the disk. So they are dilating, changing sizes, and the foreground background intensity of the disks. All right. So again, we train a deep neural network denoiser, a unit on this data set, and then we for denoising, and then we look at the eigen decomposition. So first of all, let's see what is the optimal denoising solution in this case. If the noise level is small, the optimal solution for denoising is to project, because this is a manifold, is to project the noisy image back to the manifold. So let's take this test image. The tangent plane at the point of this clean image is computed by taking the derivative of the image with respect to those 5 variables that are generating the manifold, right? So I'm showing those 5 vectors in here, basically. They result in vertical translation, horizontal translation, foreground and background intensity changes, and the change of the radius, as we expect, okay? So the optimal denoising solution from a shrinkage in a basis point of view is basically the optimal basis consists of these 5 vectors at the top with shrinkage values of 1, and then the rest of the basis is not constrained, but the shrinkage values should be 0, right? So the rest of the basis can be anything because the shrinkage values are 0 because this is a projection. So now let's see what the denoiser learns, the DeepNet learns. So these are the top 5 empirical eigenvectors. And as you can see, they match the optimal eigenvectors pretty well, or the top 5 vectors in the basis, the optimal basis pretty well. They span the same space, right? And the shrinkage values or the eigenvalues are close to 1. Now let's look at the next 5 eigenvectors. So these are the next 5 eigenvectors from the empirical basis. And as you can see, they're not arbitrary. We can clearly see harmonic or oscillating patterns along the contours of the disk and in the background regions. So more importantly, the eigenvalues for these next 5 eigenvectors are not 0. They are positive and they're quite significant. They're large, which means that the solution of the DeepNet is less than optimal because any component of the noise that is in one of these directions is going to be preserved partially, which results in a higher MSE. So what this example shows is that the DeepNet ends up learning a gap basis for denoising, even when it's the suboptimal solution. So to connect this to the first part, again, the reason that it appears that the reason that the generalization is possible with a finite set of data points is that the DeepNet is although it has many parameters, it's very restricted in terms of the class of functions that it can estimate. It always ends up learning gaps. And fortunately, gaps are a good function for denoising natural images as well. All right, so okay, so the interim summary. So we showed that the diffusion models can transition from memorization to generalization with large enough training set size. However, this size is tiny compared to what we need for estimating the density without any inductive biases. Generalization is strong. Two denoisers trained on non-overlapping training sets converge to nearly the same function. And generalization is due to an inductive bias corresponding to shrinkage in a geometry adaptive harmonic basis. All right, so now I can move to the second part. If there's there's no questions, or if there is questions, we can.
I got a few.
Yep.
I had a number of questions about the wavelet section. So when you presented the fixed wavelet and then the adaptive cutoff, is that wavelet like Haar wavelet, or which wavelet basis are you talking about?
Yeah, that can be any wavelet.
I guess wavelet is a general term, so I'm not sure. Okay, you're talking about a general framework.
Yes, I'm just talking about any wavelet. You can work out the optimal threshold.
Okay, thanks. Have you compared to like other forms of operator adapted wavelets, like beyond the inductive bias of the neural network, like operator adapted wavelets from the like numerical harmonization community or these kind of things?
So I was not comparing at all with wavelet performance, because the performance of these denoisers is way higher than any wavelet that you use. And the reason for that is, although like better, of course, like Haar is a pretty basic wavelet, so the results are not great. But even if you use smoother, better wavelets, at the end of the day, because the basis is fixed, the performance is way worse than the deep neural network denoisers.
And lastly, I might have missed it, but how are these geometric adaptive harmonic bases defined? Because I thought they were defined based on the like some sort of training data, but the last example is like, you know, the underlying training data distribution, but they learn something different. And I'm wondering, so if it's not based on the data, then how are they defined?
Right. So they're not, we don't define the geometric adaptive harmonic basis, right? Like they are emerging from the architecture and the properties of the distribution. So we have a convolutional architecture, and images have translation invariance property, both local and global. And the combination of these two results, and the training results in the emergence of this basis, right? So this is not, so we never set up the network in any ways to compute this type of basis explicitly. This is what is coming out, and we're showing that using an eigen analysis of the Jacobian.
Okay, then I'm a bit confused why you would expect generalization then, because then it sounds to me like this is some basis resulting from the training dynamics of the neural network, and then sometimes it matches some optimal basis if you know the data is simple, but then if the data is complex, you don't have a good understanding of it, and then why might you expect generalization?
Yeah, that's a very good question. So what is surprising here is that it's not that we only observe generalization in terms of the model variance going to 0. We are from the high quality, right? So when you pair the 0 model variance with the high quality of the generated images, it means that the model bias is also small, right? if it's easy to achieve generalization if you simplify your network, your function class a lot. Like you can, for example, just train a linear model on this data, and you will achieve generalization much earlier than what I showed, right? But the problem would be that the synthesized images would not look like faces, right? So because there's a lot of model bias there. So what is surprising here and what is nice here is the alignment between the inductive biases of the architecture and the properties of the underlying true distribution, right? So because both of them, I guess the local translation invariance is what is the most obvious property. Because they are aligned, then we are able to estimate a good or approximate a good density with limited data.
Okay, thanks.
I guess I'm saying like the complexities of the underlying distribution and the architectures are aligned.
So I think no questions for now.
All right. Okay. So I have 15 minutes, so I'm gonna go through the second part. All right. So it seems like now we're in good shape with learning densities. Because we showed that if you have enough data, like 100,000, it's not little, but it's feasible. We can learn a density, or we can achieve generalization. So now the question is, in this part, I'm going to ask a question about, can we reduce the size of the training set size required for generalization? So now, going back to a question, the first question from the audience, what I didn't really discuss was the number of images that we need to achieve generalization in terms of the reduction of the model bias. Aside from the complexity of the image data set, depends on the size of the image and the size of the network. So here is a preliminary result on the relationship between the number of images that we need, or the size of the training set size for generalization on the y-axis, and on the horizontal axis we have both the image resolution and the network size in terms of the number of parameters. They're growing together with a factor of 4. Okay. So as you can see, we need exponentially more data when we increase the size of the image and the size of the network. And this is what has led us as a community to build larger and larger models. Hundreds of millions or billions of parameters are now common in diffusion models. So one reason that we need larger models in order to generate larger images or train on larger images is that we need global receptive fields. So what do I mean by that? In a denoising neural network, each pixel in the output image is computed from a collection of pixels in the input image. And we call that collection of pixels in the input image the receptive field. And I'm showing an example receptive field here with this red box. The size of the receptive field depends on the architecture and the size of the network. And the type of the architecture is also important, like if you have downsampling layers or not. Now, here is an experiment. We're going to train a neural network where the receptive field of the network is smaller than the training set, the resolution of the images in the training set. So after the training is completed, we use the denoiser in a diffusion framework in order to synthesize images. So here are 3 examples of synthesized images. And as you can see, these images are failures. We don't have faces. They don't generate, the denoiser does not generate faces. You might see like features of the face in these like texture like images that are generated, but we're definitely missing the global structure of the face. And this failure is due to small receptive field size. So basically what this implies is that because this network is using local and translation invariant receptive field, it is enforcing a Markov property. So the learned implicit prior is a Markov random field. So it means that each pixel, when conditioned on the pixels inside the receptive field, is independent of the rest of the pixels in the image. And this failure shows that Markov random fields in pixel domain are not sufficient to capture the global dependencies of the face.
I'm so sorry for
no worries.
For the previous slide. Are these denoisers trained, or are they just like the?
Yes, right. So yeah, so I have a BFCNN architecture, which is 20 layers of convolutions with ReLUs and batch normalization layers.
Gotcha. And they've already been trained on like a data set before this?
Yeah,
or
so
just the initialization. Okay, sorry.
No. They haven't. We start with random initialization, and then we train the network on a data set, like a celeb A data set, high quality celeb A data set where the images are large. So in this case, the receptive field size of the network was 40 by 40. And then the images in the train set were way larger, like the 320 by 320, I think.
Gotcha, thanks.
All right, so this failure seems to imply that to generate bigger images, we have to make the models bigger to keep the prior global over the entire image. Now, that's not good because it means that in order to achieve generalization, then we are going to need really huge training sets. So in this part, I'm going to ask the question, is this really necessary? Do we really need to blow up our models in order to capture the global prior? And the short answer is no. And I'm going to show that with incorporating a few assumptions about images into the architecture, we can achieve a global prior without increasing the size of the network. So the simple intuition here is that instead of making the model bigger, we can make the image smaller. And to do that, we take a large image and convolve it with a low-pass filter and then downsample it with a stride of 2, which makes the image 1/4 smaller. But the problem here is that we lost all the details. But there is a solution for that, which I alluded to before. We can hold on to the details by convolving the image with 3 additional filters where they extract vertical, horizontal, and diagonal details. And here, collectively, they are notated by X bar. So this is a wavelet strategy, a wavelet decomposition. It's a linear operation, and it's an orthogonal transform. So we can represent it with a matrix, and the inverse is just a transpose. So now, because the transformation is invertible, we can rewrite the original image density as a joint over the low pass and of the details. And we can take it one step further and factorize the joint into a density over the low pass image, the smaller image, and a density over the details given the low pass. So up to this point, we did not reduce the dimensionality, but here I'm going to make an assumption. This is just an assumption that results in reducing the dimensionality. And the assumption is a Markov assumption in the wavelet domain that is conditioned on on a small neighborhood in the low pass, the content in the local neighborhoods of the detailed images are independent of the rest of the representation. So this results in a huge reduction of dimensionality in the conditional density. But we haven't completely solved the problem, because the density over this low pass image still needs to be global, and that image might be quite large. So we can solve this issue by repeating this procedure until the low pass image is small enough, right? And that's it. So we have factorized the density of the original image into the product of low dimensional local conditionals, because we're making the assumption, enforcing the assumption that these conditionals are local. And then we have a global density over the low pass, but this one is also low dimensional because the low pass image is small. So now, because these are all low dimensional densities, we can capture them with smaller networks. And here is how we implement it. So we build a conditional denoiser with a local receptive field to impose the Markov constraint on the details. It takes the noisy details and then a clean low pass, and then returns the denoise details. We train this using the same framework that we had before. And we build one of these for each one of these stages. Depending on how many stages we have, we build one of these for each one of them. We train one of these for each one of them. And then at the end, we also train a normal CNN to denoise the low pass image. So they all have small receptive field sizes. And then we assemble these together in order to build a multi-scale architecture where all the receptive fields are small. So first, the noisy image is fed to the network, and it's decomposed into channels by a wavelet transform recursively. And then each of these channels is denoised and combined using the inverse transform in the second half in order to produce the final denoised image. All right, so this is how we can build a multi-scale wavelet conditional denoiser with a Markov property enforced. Now, this was just an assumption, so we need to check to see if this assumption actually holds, if it's a good assumption. So first, I want to remind you that Markov assumption is not a good assumption in pixel domain. So here is a plot that shows that. Again, we have a performance of denoising plot. It's input PSNR versus output PSNR, and each curve corresponds to a denoiser in pixel domain, so just a normal denoiser with decreasing receptive field sizes. So on the top, we have the largest receptive field size, and as we go down, the receptive field size is decreasing. So as you can see, the performance is hugely affected by the receptive field size, which means that the Markov property does not hold in the pixel domain. All right, so now let's see if our assumption about locality on the details conditioned on low pass holds or not. So now we can train our network, and with varying training set sizes, varying receptive field sizes in order to see if the performance is affected or not. Most importantly, we want to see how small can we make the receptive field size in the wavelet domain in order to still have good performance, but have smaller networks. So this plot on the right shows that the performance is pretty much the same, even when we go down to 9 by 9 pixels. And this is on the larger images that I showed in the beginning. So just to visualize this, here is an example image. So we have a noisy image. This is the input image. And we can see the performance of these different denoisers on this image. So on the left, we see these restricted receptive field denoisers in pixel domain, which are operating on the noisy image. And as you can see, none of them have good results. And particularly the output gets worse as the receptive field size decreases. But on the right, we have the multi-scale local denoiser, where the performance is basically independent of the receptive field size down to 9x9 receptive field size. So again, we show that the Markov assumption holds in wavelet domain. Okay, so this is just for denoising. We can use, obviously, the denoiser in a diffusion framework, which I started with. So in order to do that, we first use the low-pass denoiser in order to generate a low-pass image from a tiny sample of initial noise. And then we generate the details conditioned on this generated sample of a face. So we generate the details, and then we combine them using the wavelet transform, the inverse of the wavelet transform, and then we get the larger, higher resolution image, and we just repeat this procedure. So the total number of parameters in order to generate this image of size 320 by 320 was 1 million, which is orders of magnitude smaller than the network used to generate a large image of this size with global receptive fields in pixel domain. So just to remind you, if you use a denoiser of a similar size in the pixel domain, we won't get a good image. Basically, the prior is not capturing the global structure and dependencies in the image. All right, so to sum up the second part, we can model probability of large images with smaller networks. The global structure is captured by a global prior over a small low-pass image, and the details can be modeled using local Markov or Markov conditional properties probability distribution, in the wavelet domain. And the connection to the first part is that there is a cost in increasing the size of the networks and the size of the image, which is larger and larger training set sizes. But there are ways to prevent that by making assumptions about the distribution and dependencies in the distribution and check them using experiments. Right, so the content of the talk you can find in these two papers. All right, that's it. Thank you.
Okay, we're a little bit over time, so maybe let's thank Zahra and let's go out for a coffee break and be back in 5-ish minutes.
All right, thank you.
Thank you, Zahra.
Thank you.